Welcome everyone. This is the second session of the EU Africa Time Zone Machine Learning Study Group for Women Who Code. So we are Women Who Code Python. And now sorry, I'm still having problems this morning. Maybe I should slurp some more coffee. It's morning where I am. I know it might be evening or afternoon for most of you, but I'm in an earlier time zone, and I clearly have not had enough coffee. All right. Our mission with Women Who Code, we are a global not-for-profit. We're dedicated to inspiring women to excel in technology careers. We have 4 general goals. We want to empower women with the skills needed for professional achievement, educate companies to better promote, retain, and hire talented women, build a global community where networking and mentorship is valued, and develop role models and support this generation of engineers. But it's not just engineers. We want to support all women who are connected to the programming and engineering field and to STEM and STEAM fields. We do have a code of conduct. We are an inclusive community. We're dedicated to providing an empowering experience for everyone who participates or supports our community. And that's regardless of your gender identity, your expression, your sexual orientation, your ability, your physical appearance, your body size, race, ethnicity, age, religion, socioeconomic status, caste, creed, political affiliation, or even your preferred programming language. We really love Python, but we understand that there is more than Python out in the world. Our events are intended to inspire women to excel in our technology careers, and anyone who is there for this purpose is welcome. We don't tolerate harassment. The full code of conduct, which applies to all of our events and online communities, can be found at womenwhocode.com/code of conduct. There is also an incident report form if you encounter anything you consider harassment at any of our events or in our online forums. We have more than just this one track. The Python track is one of 6. We also have front-end blockchain, mobile, cloud, and data science. And these tracks are our online global tracks focused around specific technical topics. We also have locale-based in-person meetups in different cities around the world. And we'd like to thank our sponsors. Without them, this would not be possible. And those are McKinsey & Company, the Python Software Foundation, Home Depot, Atlassian. These are all great companies, and yes.
Thank you to our sponsors.
Oh, I'm sorry, go ahead.
I said thank you to our sponsors.
Yeah. And this is ML Mondays, 2nd of December. So this is Math for ML Overview. It's hosted by Julie and myself. I'm Bethany. And we just want to talk a little bit about a study group thing. This is different than the webinars that you see us announce a lot of. This is less formal, and we intend this to be semi-regular and ongoing. So every other week for this time period. We also have another one of these that is in a different time period that you will see announced, and it also is every other week. So this one follows that one. We expect this to be fun, and we want to increase our knowledge together. None of your questions are stupid or silly. We're all here to learn, and we all realize that we're at different levels. Some of us might be totally expert on this, and some of us are definitely not expert on this, myself included.
Me too.
Yeah, and so we want to do this together and to explore and to have discussions together. And to, to bring resources to this group and to spark questions and to, and to compare knowledge. We intend this to be collaborative. We're interested in learning from each other and asking questions and doing collaborative work. The first few of these sessions might feel less collaborative, but we really hope as these go on that these are going to be kind of work sessions where we talk through stuck points we have or ideas we have or projects that we're working on. So this isn't where you listen to a complete presentation from an expert. And we're not going to be creating notes per se or slideshows for this study group. I mean, we do have notebooks, and we are recording the sessions, and we do have a repo for community notes and code, but this is not, again, something where you're just going to kind of sit and listen to a PowerPoint slide. And this is just a quick review from the last session that we had. What exactly is machine learning? It's an application of artificial intelligence. It provides a system the ability to automatically learn, quote unquote, and improve from experience. Experience means data, without being explicitly programmed. So it's taking what we have, which is a bunch of data, and going to what we want to know, which is predictions from data that the algorithm has not seen before. And that algorithm we call a model. It takes patterns from the data provided, so the training set, and it, quote, learns from that data. And so the more data, the more we teach the model, the more training data we feed it, the hope is the better it can predict outcomes in data it hasn't encountered. But any model is only as good as the data and the patterns it's fed, which is a concept we'll be revisiting. So I think that that is essentially all we have there. So let me stop sharing. There we go. All righty. So what we were planning to do for this session is, because we had a previous session that was a whirlwind tour of Python, and that was a lot of Python. If any of you attended that session, or if any of you are at a level where you have some questions about Python, we thought we'd take a few minutes here at the beginning to kind of work through a few of those before we jump into an overview of all of the scary math that you might encounter with machine learning, or at least scary for me. I know for a lot of people it may not be scary at all, but for us liberal arts majors who studied Russian and political economy and not computer science and calculus, it can be a little intimidating.
I'm a writer, so math, I don't know.
Yeah.
But it's gonna be okay. We're all here to learn, and hey, it's a study group, so that's why it's a study group, to learn together.
Exactly. So I can pull up the Python notebook from last time. And
maybe people, like, if you want to tell us in the chat or even vocal, what are your level, quote unquote, in Python is, like, are you used to using Python in everyday use for your job, or even as a hobby, for example? Let us know. That would be good, a good starting point, I think.
Or you can also, I think I've let everyone talk. Talking is permitted, it says in my little panel here. So you can also just give a shout out comment if you want. You don't have to type it into the chat. But yeah, just a little general thing. And meanwhile, I have pulled up the Python notebook, and let me actually put the link to the repo in there in case you do not already have the repo link. So this is the link to our repo where we're posting materials and resources and the notebooks that we're kind of coming up with. And as we get further along, there'll be probably notebooks from other resources or links to books and other materials that we are following. So yes, you can find them there. And these notebooks, you can either clone them down to your machine if you're familiar with running Python and with Jupyter notebooks, or if not, you can also open these. There are links to open these in either Colab, which requires a Google account, or Binder, which does not require an account.
Easy as that.
Easy as that. I prefer Binder because they're not for profit and they're not going to necessarily collect any data on you whatsoever. Google is Google's a little more, you know, they're really interested in what you're doing. just to be real about it. All right, let me share this screen really quick, and few more minutes, but if you guys don't have any questions about Python, then we'll go on to the math thing.
Yep.
But yeah, this is, I'm using Colab because Binder is not quite working for me yet this morning. So, but anyway, this was just a whirlwind Python tour with everything like, I don't know, strings. I don't remember, PEP 8. PEP 8 is a fun one. Yes. Comments, all of that. And you can always ask, you know, in the Slack channel, in the Learning Python channel, or in general or anywhere, you can always ask your Python questions. We're always happy to answer those and work through them.
You're welcome, Irina.
We understand that this is kind of a cyclical process. You kind of learn enough to do a thing, and then you revisit it later, and then you revisit it later, because no one can swallow it all in one big chunk. I mean, I certainly can't. I find out about the weird corners of Python every day, and I've been doing Python a while. And then, of course, oh, I'm sorry, go ahead.
There's always new things added.
There are, and actually I had a very, very funny moment last week. I guess most of the people I know who are not as obsessed with Python as I am thought I'd kind of lost my mind. But Raymond Hettinger, who is a core Python contributor, he was responsible mostly for writing the collections module, which is all these variations on dictionaries and queues and lists and things. But he's been a core contributor to Python for years, like for over a decade. And he has been lately, his Twitter account, he's been tweeting about a new feature in Python 3.8, which has just come out, that is called the Walrus Operator. And it's called the Walrus Operator because it's a colon and an equal sign, which if any of you have programmed in, I believe, is it in C++? I can't remember what other languages, but there are other languages who use this assignment operator. It's a way for you to declare a variable and assign it at the same time. So anyway, it's a new feature. I don't know all the details of it because I haven't played with it yet, but it's a new feature in Python. So last week he was tweeting about, you can do this with the Walrus Operator, and you could do this with the Walrus Operator, right? And then I also followed David Beasley, who is a Python programmer from the very beginning. He used to work for NASA, and he adopted Python when it first came out, and he's been a Python programmer ever since. And he is kind of an anarchist. And so first I see this tweet from Raymond Hettinger about this super cool Walrus Operator. And then I see this tweet from David Beasley that says, you know, most Python programmers use an underscore if they want to do a throwaway variable. But you can also do the following. And then he shows two lists of tuples, one of which says 0, 1 and hello, and the other one that says 0, 2 and Satan. And then, you know, actually I should find it because people are not going to understand it. Anyway, it was this whole long thing about like, you can do the following, and he used a bunch of like weird brackets instead of like the normal, like for item in, he used like bracket, bracket, space, bracket. You know, in list, colon, print, you know, print X, and then the interpreter came back with, hello, Satan. He's like, be different. Anyway, people, yeah, I took way too long to explain that, but yes, David Beasley's well worth following. He's kind of an anarchist. He's a crack up. All right. I missed the first session and just joined Women Who Code. Hope to learn together. Yes, we're happy to have you, Irina. We're very excited as well. So yeah, if no one has any questions about this notebook, you can always download this and work through it. There were exercises in this notebook, and there was a little bit of homework about transcripting DNA to RNA and making proteins, which is sort of a fun practice of, you know, all the basic slicing and dicing and, you know, list manipulation in Python. And so I would encourage you to, if you want to practice, you can download it and practice with it. So, all right, we will go ahead then and get to the math part of the party.
Ooh.
Yay! I've stalled long enough. It's too late. Now I have to actually do it. No, I'm kidding. I joke. All right. Sorry, I'm trying to. All right, there we go. Can everyone see this notebook?
Yep, perfectly.
Okay. All right. I'll make it a little bit bigger. And I don't know, do we want to tag team on this, Julie, or?
Yeah.
Okay. I will, I guess I'll do the first part. And
I can do the matrices if you want.
I can do the what?
The matrices if you want.
If I want. Oh, but you had so much fun with the matrices.
Yeah, that's why I can do it if you want.
Oh, okay, okay. All right. All right, okay. So we should get going with this. So mathematics for machine learning, part 1. So so we're going to get into specialized Python libraries for machine learning, and everybody quote unquote. Most people know what these are by now, because if you Google machine learning and Python, these libraries pop to the top of that search. So there's NumPy and there's Pandas. There's this thing we call the scientific Python stack, which is NumPy, Pandas, SciPy, Matplotlib, and Seaborn, among other ones of those. And those are all Python libraries that get at, well, NumPy adds more mathematical precision and the ability to handle matrices. Pandas adds the ability to basically, Pandas deals with what's called tabular data, but the way I always explain it to people is Pandas is Excel written in Python without a GUI, because that's essentially what it is. So it does what Excel does, but it does more than what Excel does, because it allows you to write functions in Python to do additional data processing and graphing. And then there's Matplotlib, which is graphing, and Seaborn, which is graphing, and scikit, which is about distributions. And so there's this whole stack of Python libraries. But before we get into those in detail, it helps to kind of have an overview grounding in math. And not all the details of the math, but some of it, so that you can kind of orient yourself. And so we don't want you to worry or panic. A lot of these are really complicated topics. A lot of people spend like a whole entire year of their college studying these. That's not necessary to get started in ML. It is necessary to kind of have a general overview of this. Mm-hmm. And then if you get excited by it, oh, by all means, go for it. Because there's a lot of really cool and interesting stuff to mine out of this. But don't be like me. When I first started this, I was like, I have to master probability. Well, probability kicked my butt. And for a while I let that stop me. Don't let it stop you. Sometimes it just takes going over these things multiple times as you move through it to get a grip. And the computer will do most of the math for you. It really will, I swear. But some base understanding that you do have to have is at the heart of the whole machine learning stack or tower is this thing we call a random variable. That's where the learning part of machine learning comes from. And in probability and statistics, a random variable is a type of variable whose value is subject to variation due to mathematical chance, probability. In contrast to other programming or mathematical variables, where a variable represents a single unknown or assigned value or data structure, a random variable can take on an entire set of possible different values, each of which carries an associated probability of it happening. Mm-hmm. So that random variable's possible values might represent the possible outcomes of a yet to be performed experience, or the experiment, or the possible outcomes of an experiment whose already existing values are uncertain. Like your confidence interval isn't very big for them. Random variables can also represent either the result of an objectively random process, so rolling a dice, a roulette table, a random walk, or a subjectively random process, because it results from incomplete knowledge of a quantity or an outcome. like the horrifying, if anybody studied probability, the first line of this problem always makes your stomach clench, which is, you know, Ed watches the weather report to see if he needs to take an umbrella with him. It's a really classic probability problem about like, what are the chances that Ed needs to take an umbrella? Yeah, those sorts of things. Horrible. I fail that question every single time. Random variables can be further classified as either discrete or continuous. So discrete is countable, continuous is uncountable. So a discrete random variable represents a countable number of distinct values. It can be quantified. So an example is rolling a fair die. So a die has 6 sides. Each one has the same probability of happening 1/6 of the time, right? As your rolls approach infinity. So each potential outcome is distinct and all possible outcomes are enumerated. The contrast is a continuous random variable is an infinite number of possible values. It is not countable. And the example I always use is a curve. You can always divide a curve in half, but then the half can be divided in half, and it can be divided in half, and it can be, and you never stop. There is an infinite number, right? You can always add another 0 to the decimal place. The values are drawn, so the values in this distribution are drawn from an interval or a collection of intervals. So here, random variable R can represent the potential height of students in a class, all of which fall within a curve-shaped set of intervals or a normal distribution. But it could be any one of an infinite number of specific numbers. And so then you go to the probability or chance of a specific student having a specific height that falls in a specific interval as being represented by an area under the curve, which is where the terrifying calculus comes in, and I'm just gonna put that out of my head. This is where you have to do derivatives, and yeah, and the symbols get all Greek, and yeah. But that really is the difference. So the big thing to take away from here is there is the discrete and countable, and there's the continuous and uncountable types of variables. So the mathematical function or formula or equation that describes the possible values of a discrete, continuous, discrete or continuous random variable and their associated probabilities is known as a probability distribution or a statistical distribution. Depends on whether you're coming in from statistics or you're coming in from probability. This is kind of at the intersection of both of those disciplines. Since all
right, and then wait, I got a question about this, and that could be maybe interesting, because when I read that, I was like, okay, so there is some probability and statistics, but what is like the big difference? And remember, from someone who has a very tiny knowledge in math, I don't really see it as statistics and probability. Seems like they are the same, but they're not. Like,
well, no, I think you're being very perceptive and very smart. And if either of our other if our other attendees want to chime in here, please do. But
it's quite complicated, actually.
I'm sorry, what?
I think it's a little complicated to explain, right?
It is and it isn't. I mean, at the most basic level, it is the difference between a mathematician who went at a problem and a social scientist who went at a problem. So the statistics, the discipline of statistics, while very solidly pinned in mathematics, its practice came from observing real world phenomenon. So you think about actuary tables, you think about you know, doing surveys for economics, you think about the collection of data, and then seeing the shapes and the patterns in the data. So and you're right that they're the same, because underneath there's still this probability, right? But the probability part of this comes from pure mathematics and the whole thing about sample set, roll of the dice, chance. And this is what makes, at least for me personally, what makes this whole machine learning and interdisciplinary, like the intersection, difficult, because you will see, depending on whether someone is teaching you statistics from the standpoint of probability, you will see the same formula written with different symbols derived from a different starting point. And if you come into it through, I took a class on edX that I highly recommend if any of you want to challenge. It's a free class. It's called, I think it's called Statistics for Social Science. I'll paste the full title into Slack. I'll look it up. But it's an award-winning class taught by two female professors. And one of them who actually does a tremendous amount of social science, like social impact research, and is like the head of MIT's Social Impact Research Center or something.
Oh, that's so cool.
Dufalo is the professor. So in any case, that class, that specific social science statistics class, uses different ways of talking about the same thing, which is that's to me what makes this very confusing is that underneath it all, it is probability, but statisticians often talk about data they've collected already, whereas mathematicians talk about the potential of the experiment.
Okay.
Does that make sense?
Yeah.
If anyone else wants to chime in with what their perspective on that is, but
yes,
yeah. So a statistician, when they talk about a statistical distribution like this normal distribution here, they might say, look, we and you can go to like the world statistics page and say we surveyed a sample of 500,000 individuals that we thought represented the European countries. And we found that the statistical distribution of height for men fell into this curve, and the statistical distribution of height for women fell into this curve. What they're not telling you is the way they selected that sample had to do with a whole lot of math underneath, which is why they qualified it by European versus not European. And why the numbers were there. But they'll talk about that, whereas a mathematician coming at it from the probability distribution will say many phenomenon in nature approach as you approach infinity in your sample or your experiment, the graph approaches a normal distribution, right? So they won't necessarily talk about the data, they'll talk about the formulas. Anyway. I don't know if I've clarified anything at all there.
Yeah, you did.
Yeah. So often you will find that that probability will talk in terms of the experiment or the sample space or the equation forward. Whereas statistics, even though they're talking about those math equations and they're talking about those principles, they're also talking about the data there as well. And then if you talk to a machine learning person, right, the reason we have to know both of these is because what we are trying to find is, based on the existing data, using the equation, can we predict or anticipate additional data, right? And so what we're trying to do is we're trying to say, if we feed it data that we think belongs to this distribution, and it learns the equation that maps that curve, can it, given new data, tell us whether or not that data belongs, right? So yeah, so that's why we have to learn this. That's why we have to go through this horrible exercise. Because of that, yes.
Got it.
So as we go further on, we're going to talk about things like cost function and gradient descent and derivatives. Derivative, of course, is the slope of a line that intersects this curve at a point. Also talking about, trying to find the area under a curve, all of those sorts of things. So there's a lot of mathematical refreshers. Again, and Julie and I try to tell each other this all the time to support each other. You do not have to memorize all of this. You just need to know enough to not be completely lost in your journey. Don't freak out. This is a lot of information. And we are going to loop back to this again and again. And if you're having any doubts, as Yashika, who runs the other session of this, says, drop them in the Slack channel. We'll deal with them.
She's the boss.
She's the boss. So with that being said, we're going to kind of touch on a lot of these topics and get on with it. Do you want to do equations, Julie, or should I?
Yeah, sure, if you want.
Okay, go for it.
All right, so let me see. Right, so we have two different types of equations. We have linear equations, which, as you can see on the graph, makes a straight line. There are two straight lines. And those equations have only one single power variables. You can see it also in writing right below the explication of linear equation here. And it's completely different to a polynomial. That's how you say in English, polynomial?
Polynomial, yes. Poly meaning many notations, I think is the rough translation of that. Yeah.
And so, as you can see on the graph on the left, it makes a curve, whereas the linear line makes a straight line. And the important thing to know about polynomial equation, it's kind of a mouthful to say.
It is.
The thing to remember is it needs to have a power more than one. And another word for power here is degree. And I think that in French we say puissance, like power puissance. So I think it's like when you have x squared, it's like the power, the square is the power on the x, if I'm not mistaken, right?
Yep.
Oh, I got it.
Yeah, no, you're doing great. Yes.
So yeah, and I'm sorry, I didn't talk about what was just above that, the fact that an equation is a combination of n variables. The variables like a, b, x, y, etc. in math, just like any variables in programming, are terms or symbols which do not have a fixed value. And the difference between this and the constant variables are do have values like 3, 5, 11, whatever you want. And so for these equations, we combine variables and constant using mathematical operation, sum or multiply, anything you want to create equations or functions.
Yes. The one that has always screwed me up, which is really, really interesting, is I don't know why the phrase quadratic screws me up, but I think because quad. So yeah, so a second degree polynomial is a quadratic polynomial, but quad is 4.
Oh my God, same thing for me. Exactly the same thing, because in French we say au carré, it's like square. So I'm like, why?
Why is it quadratic? Exactly. I don't understand.
And when we say like power 3, it's cube. I'm like, why?
Why are we going the opposite direction? Why is like 2 quad and cube is, no. Yeah. So that's where I just say, okay, that's where I just memorize this magic word and then I get on with my life because
exactly.
It just doesn't work otherwise.
That's the best thing to do.
Yay. So for me, the biggest takeaway here is that for the most part, in machine learning, if you are doing something that is non-linear, which many of your algorithms will be non-linear, then you're in the polynomial equation curve shape, and whether that curve be in 2 dimensions, 3 dimensions, or more dimensions. And so then you have all of this calculus associated with that because it's a curve. but there is some machine learning, linear regression, and you can, the linear gives you a clue there, where you might be able to coerce or find a straight line in your data. So that's where you get that. All right. So now we go to matrices, or the matrix. Yay! Matrix math, linear algebra, rocks.
I'm actually happy because I got them thanks to Yashika, because I was so stuck on matrices. I was like, oh, I don't get it. But I feel like once you get the hang of it, you got it. Once you know that what a matrix is and what it does and how to calculate them, it's okay. The more you will need more practice to get it in your head, but it's scary at first, because when I first saw that, I screamed, literally. But then Yashika helped me and said, oh, don't worry, I got it. It's just do this like that, and that's it. And she was right.
Yeah. Well, and I think that's really important to share, because of all of these things, and maybe it's simply the way my brain works, but of all of these things, if you get a solid grasp of matrices, it's super helpful for machine learning. Yeah.
Completely.
There's a very, very popular library that you all may have heard of, Tensorflow. Tensorflow is named for a 3 or n-dimensional matrix. So a 1-dimensional matrix is a vector, a 2-dimensional or more matrix is a matrix, but a 3-dimensional one is a tensor. And so the TensorFlow library is a library that's been tuned to do matrix math on matrices that have 3 or more dimensions.
That's great.
Yeah. And so, the math can get crazy. And so here again, this is one of those things where, like, addition, subtraction, and multiplication are good to have a firm grasp on. But someone asked in the last session, can you do it in 3 dimensions? It's like, yes, but that's why computers were invented. Because my brain doesn't work that way. Your brain might, and I encourage you to play with it if it does, but this is why we have TensorFlow. Exactly that. So yes, go ahead, Julie, sorry.
It's okay. So as we can see, a matrix has in here 2 dimension, height, you say height? Height and width. I don't know how to say in English.
Oh no, width is the way you say it in English. You're doing great.
Oh, height and width.
Height and width. Yep.
So it means rows and columns. That's quite important, because as you can see below that, you have the shape of the matrix, and the shape is always the rows times the columns. So here, 4 times 3, 4 rows and 3 columns. So they are very used, as I can see here, on NumPy and Pandas libraries. I'm reading at the same time. So as you say, vector, 1-dimensional matrix. I'm thinking in French, and it's difficult to talk in English.
No, that's quite all right. That is quite all right.
Yeah, all right. So you can see below the first graph, below that, the second graph, you have the row vector. So it's the first row, 9, 8, 7, and the row vector, its shape is 1 times 3. And below that, you have the column vector. So as you can see, it's the third column. And third row. Oh my God, no, third column.
Third column. Yep. No, you got it.
Third column, and the shape is 4 times 1. Yep. Easy as that.
Easy and as difficult as that. So one of the difficulties here is that when you work in something like NumPy or Pandas, this data structure right here is the data structure, and it will keep track of that for you. But if you model this in core Python, it won't print it out like this for you.
Mm.
What you end up having is a list of 4 lists or 4 arrays, right? And so it's hard to picture the square, the matrix, when what it shows to you is a nested data structure, right? Where you have 4 lists of the same length enclosed in one bigger list. But that is actually the way that NumPy and Pandas does it as well, although they're using arrays and not lists. Arrays are contiguous in memory, so it makes it faster. But it is the same, it's the same thing. And that's why shape is important, because NumPy, as it turns out, NumPy and Pandas, they store everything flat as an array of arrays, but then they store a piece of information that is the shape, so that the program knows, sorry, I'm struggling a little bit here. The program knows the order of precedence, right? So like this column vector, that column vector, you want it to be shape 4 by 1 because it is a column vector. But NumPy, Pandas, and Python are all going to store it as if it's a 1 by 4, right? There's no notion of like a column separate from an array. They're all arrays, but the shape says, no, this is column wise as opposed to row wise. And that's probably too much detail, but but that's why there's this thing up here about it's always a series of arrays. Yeah, so that's the shape, and it's always row first. The first number is always the row count. And then we have rank.
For that, I mean,
yeah, exactly, a sigh.
like it depends on the dimensions. So one dimension is only one vector, right? If I'm not mistaken. And here, since you have 3 columns, then you have 3 dimensions. I think it's because you have 3 columns, but I'm not sure.
No, dimension has to do with 3 dimensions is so you have height, width, and depth. Right?
Yeah. Oh, right. Sorry, I was thinking in 2D, right.
No, but that's why I sigh when I say rank, because it's hard enough to remember dimension, and then they introduce this new word called rank. So I usually fixate. My personal default is to default back to, is it a 3 by 3? Is it a 3 by 3 by 4? Is it a 3 by 4 by 5? And not try to, these words, oh, sorry. These words confuse me, but that's me. I mean, the name of the game here is whatever helps you kind of grasp the concept, right? And grasp what you're reading. But for me, I rank and dimension are problems for me word-wise.
Yeah, me too. I don't get them. Like, because what's a dimension then? Like one vector is one dimensional matrix, as I can see just below, above, sorry.
Right, and then a matrix is 2 dimensions.
One matrix is like, this one is 2 dimension or 3?
2. So a vector is a 1 dimension. A matrix is a 2 dimension. So a 3 dimension is 1 layer back, right? So if you think of a Rubik's Cube.
Oh.
So one matrix is 1 face, right? But in a Rubik's Cube, you have like 3 going backwards. So that has 3 dimensions.
Okay.
But then, of course, you know, very quickly in machine learning, you get to what's called n dimensions. So you stack, right? If you think of an Excel spreadsheet, that's another one I use. If you think of an Excel spreadsheet with multiple tabs, right? You add one tab that's 3 dimensions, but you add another tab that's 4. And then all of a sudden you can't imagine it in real space because it doesn't exist in real space anymore. And that's where I just kind of like, those words start to not make any sense to me.
Yeah.
I start to rely on numbers to tell me, right? So this number tells me how many rows. This number tells me how many columns. This number tells me how many layers deep.
Oh, layers, that's a good word. Oh, yeah.
Yeah.
Okay.
And rank and dimension for me don't help in that visualization.
Mhm.
But for some people they do. but maybe it's because I'm not coming at this from a mathematical perspective, but it just doesn't like, it's like, yeah, nah, I'm gonna ignore that. But yeah, and it's, oh, go ahead, I'm sorry.
I was saying, like, if you see them in layers, that quite helps me actually, because I couldn't see them before, but oh, right. Layers,
And
okay,
so,
I noted that.
So layers, and so it's quite possible to, so you know how here we're taking a slice off here or a slice here.
Mm-hmm.
So if you think about it for a minute, if this were 4 layers deep and I took a core sample at 30, that is also a vector, but it's a vector along a different dimension.
Oh.
Yeah. And so that's also another thing that TensorFlow allows you to do, is it allows you to do operations, and Pandas allows you to do this as well, to do operations that way as well, through the layers as opposed to, you know, across one layer.
Mm-hmm.
Yeah, so that's something to keep in mind. And this was at the point in our last session where somebody said, oh, so you can do multiplication across 3 dimensions. And I'm like, sure.
Oh,
I'm not gonna.
sure.
I'm not gonna show you how to do that manually because my brain won't work that way. So you can look at addition and subtraction, because addition and subtraction are pretty straightforward, but multiplication is a little bit tricky here with matrices. So
yeah.
All right, so here we have matrix multiplication, and we've got a bug in this notebook. For some reason, it did not like my LaTeX formula. So let me do something really quick here, which is I'm going to try the binder book again. Bear with me. My apologies, people.
No problem. If you have any questions, you can ask us in the chat, because hey, it's a study group. So if you're like us, still learning.
Exactly, and we've been blathering for quite a few minutes now, so.
And that's why we're learning matrix.
Yeah. All right, so binder is cooperating, yay! All right, okay, so here we have our matrix explanation, and here we have matrix multiplication. So,
all right.
Go ahead.
I said, all right.
All right, so here is the deal. So the rule here for matrices is, for multiplication, is that everything has to happen pairwise. Yeah. So every element of one matrix has to be paired with an element of the other matrix. And if you cannot make a pair, you cannot make the multiplication happen.
Mm-hmm.
So you do a dot product. So we'll start with the simplest, which is 1, 2, 3 times 7, 9, 11. 1, the first position goes with the first position, the second position goes with the second position, and the third position goes with the third position.
Yeah.
Add those together. But then it gets a little more complicated if you've got more than one dimension. So here's one where we've got A, which has 2 rows, and B, which has 3 rows and 2 columns.
Mm-hmm.
So the first step is, essentially, we make vectors out of each of the things that we're going to multiply together so that we can perform this operation. So we start with the first row and the first column.
Mm-hmm.
So we get 5.
And I think it's important to note too that it's always row times column, always.
Yes. And so if these two, if this matrix was lined up so that it had 3 rows and 2 columns, then you would want to be taking, right, it would be a different, actually, I don't think you could multiply those together, could you? Let's see. We have 3 by 2 and 3 by 2. You wouldn't be able to do that.
No.
Yeah, it doesn't work. So row, column, first one. And then row, second column for the second one.
Yeah.
And then we go to the second row, but back to the first column. And then we go the second row to the second column. And so here you can see that's the product.
Yes.
And because of the specific order of this, it's also important to remember, and this one is very hard for me because in my basic math class, I was drilled that multiplication was transitive, meaning you could A times B equals B times A.
Yeah.
That is not true for matrices. Absolutely not true for matrices. You cannot do that and expect the same product because of the way these things are, the order of the way these things are multiplied. Yes, there are rules. You cannot forget the order. So the way I was taught this is a little bit different, I think, Julie, from the way you and Yashika were taught this. I was always taught that, so a matrix is M by N. M is the number of rows, N is the number of columns, and when you multiply, N needs to match. So the internal dimension needs to match. But the way you and Yashika learned it is also valid. It's just another way. It's another way of looking at it, right? But here you always have to get these two numbers to match, or it can't happen. So if you see here, these match, so you can do it, and you get, and that's the other thing. If this number here is a 3, then this matrix is going to be a 2. If it's a 5, then this is going to be a 4. It's always, the product is always one less than the n dimension of the two matrices.
Oh, I didn't know that.
Yeah. So that's a nice shortcut. I don't know what it necessarily gets you in the grand scheme of things, but that's one. So if I know that the matrix is like 2 by 5 multiplied by 5 by whatever, then I know the result is going to be a 4 by something. Yeah. So what you can't do though is you cannot do this. So notice this, a 3 and a 2, they don't match. And so if you think about it and you think about the order of multiplication, right? You take this row and you take this column. Well, there's one number here that does not have a matching number here.
Yep.
It's not defined and it doesn't work. But this, this is a really nice shortcut too here. The columns at the left must equal the number of rows in the right. Right.
That's a good shortcut. Yeah, it helps.
Yeah. So there's a lot of practice problems that you can do with these, and there's actually a book called Coding the Matrix, which I recommend if you want to do like a linear algebra kind of geek out or deep dive, that has some fun exercises in core Python around kind of this sort of thing. But for me, the general rule of thumb is it's not that you need to know how to do these complicated things in your head. It's more the concept of, a lot of machine learning is around matrices of what's called features, which are the data. You put the data in a matrix, and then you perform different transformations on those. And so it's helpful to understand the basics of this. And then there's all sorts of special matrices, which we might dig into further, like the identity matrix. And so sometimes what you can do, so this is all the happy path, right? Where the n dimension matches so you can do the multiplication. But chances are good, you're going to encounter something where you want to multiply it together, but one of the matrices isn't in the right shape for you to do that, right? And so there are things that you can do, mathematical transformations that you can do to get the matrices in the shape that you want. One of them is using an identity matrix to transform something, or you transpose the matrix in order to be able to multiply it together. So we'll be going over some more of those later.
Oh, that's so cool. I didn't know that.
Yeah. So you can get tricksy with it. Or you can ask the computer to do it for you.
I like that. I like that option.
Yeah, me too. I'm all for that option. All right. So the next, and we'll probably have to wrap up here in the next few minutes. But the next little thing we're going to touch on, of course, is probability. I'm not sure I'm going to say a whole lot here, except.
Me too. Honestly, me too, because probability is, in theory, complicated because you have all the equations and everything. But this example below is quite understandable because it takes the example of coin toss.
Yep.
And you know that you have a 50-50% chance to have heads or tails. And it's still quite complicated to me for now because there are so many terms to know and to understand that understanding all the distribution, and even further down this document, there are so many things too that are complicated when you don't really get beforehand the terms correctly. So yeah.
And the thing, one of the, and I can paste this link in later for the resources, one of the hardest things for humans in general to understand, and me specifically to understand, is this infamous thing called the Gamblers Fallacy. So when we talk about coin flips as being a 50% probability, we mean that if we were able to do an infinite number of coin flips, then the distribution of the results would approach 50% for heads and 50% for tails. Yeah. However, in any given increment of time for any given set of coin tosses, that does not in any way, shape, or form mean that you will get 50% heads and 50% tails. In 100 coin tosses, you might get 100 heads. And that is not an unfair coin. That just means that wherever you are on the infinite set of coin tosses, you have a streak of a bunch of heads. So for me, it's hard to remember simultaneously that each coin toss, each time you toss the coin, it's a brand new world. Okay? It's a brand new world. It's what's called an independent experiment. And so you have a 50-50 chance of it coming up heads or tails. But the next time you toss the coin, the world resets.
Yeah.
So that does not mean that like in 2 coin tosses, you'll get 1 head and 1 tail. Because they're independent. Yeah. Anyway, I fall for it every single time, right? Like you can't, like if somebody tells you like in 500 coin tosses, I got 350 tails. And it's like, okay, well, you happen to get 350 tails. That doesn't say anything about the probability that the next coin toss is going to come up tails. Yeah. So anyway. but that is also an illustration. Those 350 coin tosses is an illustration of what we call the sample space. Right? So 350 coin tosses is my sample space. The probability stays the same, that each coin toss has a 50-50 chance. But when the results are tallied up, you might have a distribution that is not, that doesn't match 50-50. Right? So yes, and so this is where the random variable part gets complicated. So you have the sample space, and the random variable represents the randomly chosen values from the sample space, each with an equal probability of occurring. And that's all I'm going to say about probability for now.
Yeah, me too. Honestly, yeah, because you guys like maybe knows if you guys want to share with us how you deal with probability and how, even if you have some, how to say, easy way, quote unquote, to learn this or to help us understand it, because I think it's one of the things you always kind of know / learn probability in your life, you know, or you always hear about it, but to apply it is completely different, I think.
Yep. Yep. And again, just like with equations and with matrix math and with the calculus, the computer can do a lot with this, but what you have to do, or not you, but what I have to remember about probability is when something is independent versus when something is not independent, when it's contingent on another event, and learning to separate those, because if you can't effectively separate those, then you've introduced horrifying bias into your models. So that's the part where you need to understand enough about probability to say, look, I'm looking at this kind of distribution, and I know that this is dependent or is not dependent on something else.
And do you know if a coin toss, is independent or dependent?
It's independent. So this is, you had questions about the Bernoulli distribution.
Yeah.
And the Bernoulli distribution, which we're going to go over distributions right now, actually. That's a great question. So continuous versus discrete. So Bernoulli is discrete. You can count how many times a coin you toss the coin, right? It is discrete. And for Bernoulli, Bernoulli represents one and only one event. It's a single experiment, okay? And so for a coin toss, this doesn't actually represent a coin toss. This represents what you would call a biased coin toss. Notice, because this is not 50-50. So let's say the coin is unfair. I toss it once. I have a 69% chance that it's going to come up heads. And I have a correspondingly, what is that? A 29% chance that it's going to come up tails. If this represented a fair coin toss, these both would be at 0.5. So Bernoulli represents a discrete distribution of the result of a single independent experiment.
Yeah, independent, so.
Independent. And this is where it's very, very tough, and I find myself making a mistake. I have to remember these are independent. Right?
When it's, like, sorry, I'm cutting you. When it's independent, that means that you don't have, how do I say this? You can't influence the results because there's a part of chance, maybe?
Independent means, so there's another famous, or at least in the United States, there is a famous story about, it's called the Monty Hall problem. And Monty Hall was the host of a televised game show. And I can't remember what the televised game show is, but you can Google the Monty Hall problem. In any case, at some point in this game show, the contestant is shown 3 doors. Behind 2 of the doors are goats. And behind the 3rd door is a really fabulous prize.
Okay.
And they are, they're supposed to choose the door that has the prize. And they're shown the goats and the prize, and then the doors are mixed up. And then, and this is just brilliant, they'll choose a door, and Monty Hall looks at them and says, now there's 2 goats and there's 1 car. Are you sure that's the door you want?
Okay.
and the person says, yeah, no, that's the door. And I can't remember how the whole setup goes, but in any case, there's this whole thing around, are their odds better if they stick with the door that they have, or if they change their minds and pick another door? And it has to do with the independence of things. So each one of those doors, there's no dependency, right? So if you pick a door, you have a 1 in 3 chance of winning.
Yeah.
And if you pick another door, you still have a 1 in 3 chance of winning. Oh, that's what it is. So he says, well, we'll take away 1 door. Now, do you want to switch? And the answer is yes, you do want to switch, because it's independent and the probability of it being any one of the doors is the same. But if you take away one of the doors, then you still, you know, switching over the long term, you still have a better odds of winning if you switch doors. Anyway, the whole, and I may not be explaining it quite correctly, but the whole point is that every time you make a decision, if the probabilities are independent, then the probability stays the same. So the next time you flip a coin, it's still 50-50. It doesn't matter what happened before, right? That's what independent means. Whereas dependent means if I, you know, if the last coin influences the next coin, then the probability changes. Yeah. Sorry, I probably blew that entirely, but but that's the whole notion, right? So you know, if future probability changes based on what happened last time, then the whole math changes. Whereas if the experiments are independent, then every time a decision is made, it's made without knowledge of any of the other decisions.
Oh, I see.
So if you were navigating a maze, you know, whether or not you turn left or right might have to do with whether or not you turned left or right before. But when you're tossing a coin, every time you toss a coin, it doesn't matter what happened previously.
Yeah.
Oh, if anybody else has a better explanation, please rescue me from myself, because I have a feeling I didn't do very well on that at all. But yes, so this is what is at the heart of the Bernoulli distribution, is one experiment once. And what is the probability?
Only once.
Only once. And then this one's a little weird. So the next one is a uniform distribution. And uniform distribution looks like it's discrete, but it's actually continuous. And what a uniform distribution is it's any value between a stop and a start. Any of an infinite number of values between a stop and a start. So when something is uniformly distributed, it is the same probability between two values, any value between two values with the same probability. And this one's used often, you know, in like stochastic programming, where you say, pick, you know, if you tell Python, I want a random choice of any of these 10 values, right? In some sense, that's picking from a uniform. I mean, it's really kludgy, but you pick from a uniform distribution. So that's the uniform distribution. And then we've got the binomial. So the binomial is a discrete distribution. And basically it asks the question, what if we ran thousands of Bernoullis? So any one of these is a Bernoulli, but collectively, if you run more and more of them, they start to be a binomial.
Oh, so that's interesting, because the first one, the Bernoulli, is only once, right?
It's once and once.
Oh, and this one you can take multiple Bernoulli distribution and run them again and again, or only once and there are many, many of them?
So here's where independence comes in.
Ah.
So one of these is a Bernoulli.
Okay.
But collectively it's a binomial. But every time you run a Bernoulli, it is independent, right? So that's why you have this set of different points, and it looks like it's making a curve. And if you ran an infinite number of them, depending on whether or not, say, this coin toss was fair.
Yeah.
So say this coin toss was fair. And this starts to represent an infinite number of coin tosses, which starts to be distributed, right, in an interesting sort of way as you get more and more and more and more of them. Actually, this would probably not be this many because this is more than two, but yes. So Bernoulli's, every time that Bernoulli is run, it's independent. So it doesn't matter what happened before. But if you just continuously plot all of these, then it starts to be distributed in a pattern, which is the binomial distribution.
Okay, so that's why collectively it's a binomial distribution.
Right. But singularly, it's a Bernoulli. Right. So the possibilities of the same event occurring more than once.
Yeah.
Then it's a binomial. There are two possible outcomes, but every trial is independent in its probability outcome. So that's, and that's the really, this one is really hard for me to wrap my head around, because you look at it and you say, well, let's make this pretty curve and let's make this pretty pattern. Yes, but every time you run a new experiment, it's a brand new world and the probability is independent.
Okay, so each line that we see is independent from the other ones. Okay, I'm taking notes at the same time.
No, I mean, this one is very, very tough. Yeah. It's very, and I might be muddy in my explanation because it's tough to remember. It looks related because it's on a picture, right? It isn't related. Every time you put a new data point on here, it is an independent experiment. Collectively, they do form a pattern, but the experiments themselves are independent from one another.
Okay, I understand better.
Oh, good. I'm glad.
Really?
I don't. Oh, and I apologize, guys, because I think we're actually 5 minutes over. So I'm going to rush a little bit, but I want to remind everyone, or if you want to stay, you can, but I want to be respectful of your time. But I also encourage you to drop into our Slack channel and ask questions about this notebook and about these concepts, and to let you know that next session we'll be interacting with code a little bit more around these concepts. So don't feel like you have to memorize all of this based on like some abstract pictures and some blathering of a crazy lady. We will have more opportunities to go over this in more detail. But that we just have, we have two more, and I'll just quickly kind of gloss over these. So this is the binomial, and then we've got the normal Gaussian or Laplace Gaussian distribution. This is something that we've heard about probably our entire lives. The bell curve, because it makes this continuous bell curve. This is a continuous distribution. So this, the values in this are not countable. And what makes it normal is that there is a mean which runs down the middle, and something is said to be normally distributed if you can actually carve it up into these sections, right? So the curve might not always look exactly like this, but if 34.1% of the values fall to the right and 34.1% of the values fall to the left, you've got a normal distribution, is essentially what this means. The other thing that you can judge a normal distribution by is you've got these things called
sigma.
Yes.
Yeah.
the sigma, which is also called the standard deviation if you're using statistics speak. I think sigma is the probability or mathy speak for this. And what this means is, okay, so remember, this is a distribution of infinite values. So if the mean or the average or the mode, right, is at the 0 point, a standard deviation, right, is if you take all of the values distributed and you divide them into increments, one standard deviation is one step out from the center of this. So a normal distribution, 68.2% of all of the values are within one step out from the center. And then you go 2 steps out on either side, and that's 95.4% of all values. Right, so that's virtually everything falls within 2 standard deviations. You go 3 out, and that's 99.6. So it's very statistically unlikely that you're at the far ends of these. Statistically speaking, right, chances, and chances are good, your highest probability is that you fall within 1 standard deviation from the mean. So that's what all that scary math over there means. and that integral, which is just terrifying, right? Over here, the CDF, the cumulative distribution function, that is a very, very schmancy ass way of saying the equation that when you graph it,
makes a curve.
Makes that curve. Yeah, that's essentially what that CDF is, which is terrifying mathematics. But yeah, so that's the normal distribution. And then, I apologize if I'm going too long for people, the Poisson distribution. So Poisson is hard to get your mind around. Poisson in French, I hear, is fish or fishtail.
Yeah, poisson.
Poisson. So, and this supposedly makes, I don't know, a fishtail.
Like waves. It looks like waves.
Yeah. So the difference between this and the binomial is that the binomial is discrete, right? Coin toss, yes, no, yes, no. Poisson is continuous.
Oh.
So Poisson has an infinite number. Binomial has a discrete number. So the binomial is based on events that have a fixed number of attempts, right? They're countable. Poisson is an infinite number of attempts, but in a fixed amount of time. So the one that I think of most when I think of Poisson is bus arrivals or a meteor shower.
For what?
Yeah. So, you know, it's infinitely, there's an infinite number of buses possible, but in this 15-minute window, 4 arrive. Or, you know, there's an infinite number of meteors that could fall to Earth.
Yeah.
But for this hour, this many happen. So usually what you hear, you learn about Poisson, but usually what you hear in machine learning is time series. Is usually how this is reduced. Do you have time series data? And time series is usually a clue to you that you're looking for something that is Poisson distributed.
Oh, cool.
Right? Does it recur, you know, how many times does it occur in an increment of time? Or multiple increments of time. Yeah. But yeah, more terrifying math, as you can see here. But this symbol here is summation.
Yeah.
And that is another clue here, right? So essentially what they're saying is for a time interval, the sum of, or the area under this curve, the sum of all events that happen then, the sum of the probabilities of all of the events that could happen then is actually what that means. Not that did, but could, right? So because again, this is about probabilities. So you have there's a certain probability in this time period of these events happening, right? And the probabilities, right, form this curve. And so what you say here is, if, you know, it's the summation of everything under there.
Yeah.
And that, and with that, I'm 15 minutes over, but with that, that kind of concludes the crazy math review. So thank you for attending this. And if you want to get involved, we're always looking for leads and evangelists, and just people to come in and make our Slack channel happy and cheerful and ask us a bunch of questions, because, you know, that's what we live for. So you can do that at wimpycode/Python. And you can also join the conversation. We have a Twitter account, we have an Instagram account, and if you scan that barcode right there, or that 2D barcode, that is an invitation to join our Slack channel, although I think you both are in our Slack channel. So
nice.
Yes. Thank you again. Apologies for going 15 minutes over. And hopefully as we go along, this will be a little bit more interactive. And we want to encourage you to ask questions and to bring things you're excited about and bring your expertise to this as well. Thank you. Bye.
Thank